Hello, and welcome back, everyone. Today we're going to be talking about sets. So, roughly speaking, a set is just a collection of some stuff. But to write down a definition that sort of sounds like a math definition, I'll say that a set is a collection of objects which we call elements. Now, most of the time these are going to be mathematical objects, so we aren't usually going to have sets that, for example, contain zoo animals or whatever. But the objects certainly don't have to be numbers. So sets could contain numbers, but just as easily they can contain matrices or vectors or even other sets, etc. So we're really not putting any restrictions on the kinds of things that can belong to a set. So how do we describe a set? Usually when we go to describe a set, we describe it by listing its elements. So I'll take, for example, this. Here I'm defining capital A to be the set whose elements are 1, 2, and 3. This isn't always the case, but it's usually the case that things that are sets are denoted by capital Latin letters, usually starting at A, but of course you can start wherever you like. Now, I want to stress again, there's no sort of requirement on the types of things that show up. So we could well have a set which contains 2 numbers in a matrix. That's fine. I also want to point out sets don't have to contain a finite list of elements, so it is fine, for example, to have this set, which contains the positive odd integers. So this set contains an infinite number of elements. These 2 sets contain a finite number of elements. We'll call these 2 sets finite and this set infinite. I want to note, something like this is totally legitimate. I have defined a set here by writing this down. But this set is exactly the same set as this set. And that's because sets have no notion of multiplicity. Something's either in the set or it is not in the set. And so once I've listed 2, 2's in the set. Listing it again doesn't change anything. So sets have no sense of multiplicity. In terms of notation, if I want to express that something is an element of a set, I will use this kind of notation. This is read 4 is an element of B, or 4 is in B, whichever way you like. This is intended to look like an E to be short for the word element, if you're curious. If, on the other hand, we want to express that something's not an element of B, use the same symbol but with a slash through it. The times when all of this get most confusing are when we have sets which contain sets as elements. So this set in particular has 4 elements, 1, 2, 3, and then the 4th element is the set that contains 1 and 3. So it would be correct in this case to write something like 2 is an element of C. It would also be correct to write 1, 3 is an element of C. All this means is the set 1, 3 is one of the things that is listed as being a member of this set. Now, if I look at something like D, it is true that 3 here is an element of D, but, and this is important, 4 is not an element of D. 4 is an element of this thing that is an element of D, but 4 is not itself an element of the set D as I've defined it here. Okay, so make sure you distinguish between these things. There are some particularly important sets that we give special names. So the first of these, which we'll denote by this is the empty set. That is, it is the set with no elements. Next up, we use this. This is probably one you have seen before in calculus classes or whatever. This is the real numbers. So for example, things like pi, or negative 2e, etc. These things are all elements of R. C, which we're not going to use too often in this course, but this is the set of complex numbers. So this is the things that look like A plus BI. Going back to one that we will talk about a lot, Q, this is the set of rational numbers. So it's a rational number. It looks like P over Q, where P and Q are integers. And Q's not 0. So for example, -3/7 is a rational number. These are also the numbers that, if you think about their decimals, have a repeating decimal, or finite decimal, which I guess is a repeating 0 at the end. So that might be how you're used to thinking about these. But they're numbers that can be written as fractions, where the numerator and denominator of the fraction both happen to be integers. Now, the obvious question is, if I sort of follow the logic here, real numbers are, complex numbers C, why are rational numbers Q? Well, it couldn't be R, because rational starts with the same letter as real, and so they went with Q for quotient, because these are fractions. So Q stands for quotient. That is why Q is used. Next up, we have Z. This is for the set of integers. Really, this is that set. So integers, not necessarily positive, could be negative, could be 0, or whatever. You might also call these whole numbers, or maybe you only call the positive ones whole numbers. It depends. But anyway, these numbers are called the integers. So why Z? Well, I is a pretty awkward letter in math to use to represent something, since there's imaginary numbers and all of these kinds of things. So I couldn't really use I for integers, although you'll see every once in a while someone will. But this Z here is short for Zahlen, which is the German name for integers. So in general, when the first letter of something in English doesn't work, we'll just grab another language. Like, for example, how we use M for slope, because M is the first letter of the French word monter, which means to climb. But if we used S, it would look awful, because S's look like 5s, so we can't use S for slope, so we borrow the word from French. You'll sometimes see additional, what I'll call, decorators on these sets to describe pieces of them. So, for example, I will very often write Z+. This is the set of positive integers. In a similar fashion, if I write Z subscript greater than or equal to 0, this will be the set of non-negative integers. So note these two things are different. And the difference is this one includes 0, but this one does not include 0. And you'll also sometimes see these sets referred to as the natural numbers. However, the problem with the phrase the natural numbers, and the reason why I avoid that description, is that no one quite agrees which of these is the set of natural numbers. In some sense, this comes down to the debate of where you start counting things, which you may have seen that computer scientists pretty firmly like counting things starting at 0. So they'll typically refer to what I would call the first entry of an array as the 0th entry of the array. So computer scientists would definitely rather work with this set, whereas then lots of mathematicians would prefer working with this set, although slowly over time a lot of mathematicians have kind of admitted that computer scientists are right, that it's often better to start counting at 0, so now a lot of mathematicians use this set. Whatever, if you pick whichever one works nicer for the particular situation, I think you'll be happier in life. Note, you could also do things like this for the negative real numbers. So you'll see all variations of this just used to describe some particular set. Additionally, we have this idea called the cardinality of a set. And the cardinality of a set is just the number of elements it has. And just as a matter of notation, we denote the cardinality of a set A by putting absolute value bars around it. So, for example, the cardinality of the set 1, 2, 3 is 3. And likewise, the cardinality of some set like 2, 4, 6, 8, that would be 4. We're going to make a temporary agreement that if a set has infinitely many elements, we're just going to write infinity for its cardinality. But go ahead and note, in a few weeks, we're going to change this. So for now, we'll write something like the size of the positive integers is infinity, or the size of the real numbers is infinity. If you're curious of a preview, why are we going to change this later? The reason that we're going to change this later is that even though, of course, I would agree there's infinitely many positive integers, and there's infinitely many real numbers, it's going to happen that these infinities are, in a sense, will make precise not equal. And so as a result, when we want to talk about the size of infinite sets, there'll be a more refined and nuanced way to talk about that, but we're saving that for later in the course. Again, I just want to explicitly call out that we call a set finite if its size is strictly less than infinity. So all I'm saying here is that the size of A is 0, 1, 2, 3, 4, ... but not infinite. And if a set isn't finite, we call it infinite. Another weird bit just of nomenclature is that for some reason we pronounce this word finite, but this word infinite, and we just have to deal with that and not pronounce this word finite, or not pronounce this word infinite, even though clearly that's where the word comes from. We're very often going to want to talk about how two sets are related, and so this is going to be through a concept that we're going to call subsets. And so we're going to call a set A subset of the set B if every element of A is also an element of B. Just as a matter of notation, we'll write this as this. This means A is a subset of B. So for examples, 1, 3 is a subset of 1, 2, 3, 4. That is a subset of the positive integers. That is a subset of the real numbers. Just for example. Note this is directional, so definitely the real numbers are not a subset of the integers, for example. I want to make a note here about the way mathematicians write definitions. And the thing I particularly want to note is the use of this word if. Most definitions a mathematician will write down will have the form, we call a blank if, followed by some condition. And if you followed the last section carefully, you got a really precise sense of what the word if meant. And so you might read this as being a directional thing. However, in the case of definitions, for whatever reason, when someone says if, linking the thing that is being defined to the definition, this if really means if and only if. So really I'm saying, if this is true, that every element of A is also an element of B, then we'll say A is a subset of B. But I am also saying if it's not the case that every element of A is also an element of B, then we will not say A is a subset of B. And if you were to read this sentence literally, it does not say that. But that's what it means. So be careful with this if being used as a linking word in a definition. It's going to be used much differently than when it's being used in a statement of a proposition or theorem or what have you. Okay, I want to make a note here that follows from this definition, but that you might miss, which is that every set is a subset of itself. So A is always a subset of A. Every element of A also happens to be an element of A. That's all this is saying. Now, sometimes you want to specify when you say subset that you mean subset that's not the original set. as in you've actually thrown at least one thing away. And for that, we use the term proper subset. Again, this if is a linking word, and you can already see we're using our and operator from before. This is starting to look more and more like the kind of logical language that we talked about in the last section. But here, by proper subset, we mean that it is a subset, but it's not the set itself. And again, just as a matter of notation, how do I write that A is a proper subset of B? I write it as this. So the way you're supposed to read this is this subset, the regular kind, is saying it's a subset or it's equal, and you're supposed to sort of see this imaginary equal sign down here, and then you're supposed to see this slash through here as saying it's a subset, but it's not the equal kind of subset. Very brief aside on notation, you will see this done lots of ways. So various people will use this symbol to mean either A is a subset of B, meaning they use it to mean that, or A is a proper subset of B, in which case they use it to mean that. You'll also see things like an explicit equals called out under the symbol, or an explicit equals with a cross through it. There are all sorts of variations of this you will see. The reason why I have defaulted to teaching you this notation and this notation is that no one who reads this or this will misunderstand what you mean. Whereas if someone writes something like this, they could well mean multiple things by it, and I always prefer clarity over that kind of ambiguity. The more complicated a set that we want to describe, the less likely it is I can easily describe it by just listing out the elements. So for example, if I wanted to describe the set of irrational numbers, it would be not very easy to say, oh, well, this is the set of pi, comma, e, comma, square root of 2, comma, square root of 2 plus square root of 3, comma, that's not really going to work. So we have a specific notation that we use to describe subsets. And this is always going to look like the set of something in A, and then a bar, and then some description. And so let me give you several examples of using this so that you can understand what's going on here. So first of all, note this thing is always describing a subset of A. So in this case, I'm describing a subset of the real numbers, and I'm describing the subset of the real numbers that is non-negative. So this is exactly, in fact, the thing that we before denoted by r greater than or equal to 0. So here, I'm describing the set of x in the real numbers. And again, you're always reading this bar here as such that. And so this is the set of x in the real numbers such that x squared is 4. So I'm describing here all the solutions to the equation x squared equals 4 in the real numbers. And so that will work out to be the set minus 2 plus 2. Note all the parts here are important. Now I'm describing the set of x in the positive integers such that x squared equals 4. And note that although minus 2 is a solution to this equation, it is not a solution to this equation that is in the positive integers. And so as a result, this is describing just the set positive 2. By the way, this unary plus is just for emphasis. Plus 2 and 2 are the same thing. Again, just to write down some more examples here, I could describe something like this. Okay, and so this is the set of real numbers that are between 1 and 4, including 1 and 4. So this is the thing you probably would have learned to write as this interval with a closed braces. So again, these things are always generating subsets. So if I describe the set of p and z plus such that p is prime, p plus 2 is prime, I know the thing I'm going to list is going to contain only positive integers. And if you take some time, you can figure out, okay, well, it contains 3 because 3 is prime and 5 is prime. It contains 5 because 5 is prime and 7 is prime. It does not contain 7 because although 7 is prime, 9 is not. But it would contain 11, not 13, not 15. It would contain 17, but not 19. Would contain 29. And so on. So you can really use this notation to describe some fairly complex sets. But note, the more complicated your description is, the less you might know about this set. So for example, in this case, I certainly have no idea how many elements are in this set. So if I go ahead and call this set, say, T, it is not at all obvious what the answer to the question, how many elements does T have, is. In fact, actually, this question, how many elements does this set I just described have, this is in fact an open question, meaning no one knows the answer to this question. This would be all well and good, but we have a different, similar-looking notation for making sets, which I'll call the set generator notation. And this will always look like some stuff, bar, and then something in some set. And so, as an example here, I can give you something like the set of n squared plus 1, where n is in Z plus. And so now what I'm describing here is rather than describing a subset of this thing, as I was up here, I'm now describing, hey, these are the outputs that you get by plugging this number in. So this is really describing the set where I put in 1 for n, which would give me 2, 2 for n, which would give me 5, 3 for n, which would give me 10, 4, which would give me 17, and so on. Note, it's a sheer coincidence that in this instance, this ended up actually being a subset of Z+. I could just as easily have taken this, in which case this will be the set of all things that I get by adding a half to integers, which would look like this. Again, people often get confused between these two different notations for describing sets. The key to distinguishing them is always going to come down to which side this description is on. So here are two sets I've described, one in each of the two notations for sets that we've described. I'd like you to pause the video and think through what each of these sets is. Okay, so first of all, which of these is which? This is the thing I called set builder notation. Since I'm saying here that I'm taking the collection of real numbers with this property. Whereas this is the set generator notation that we talked about second, where I'm saying plug in everything here to get everything over here. If I go ahead and write this as A and this as B, then I can figure out, okay, what is A? So it might take you a second. This is what I get when I plug in every number between -4 and 3 to x squared plus 1. So I get numbers as large as 17, because if, for example, I square -4 and add 1, that would give me 17. But I, in fact, get out numbers as small as 1, because if I plug in 0 here, I actually get out 1. So, in fact, actually, the A I've described here is the closed interval from 1 to 17. If you want to picture this graphically, here's the function x squared plus 1. Here's -4. Here's 3. The numbers that I ended up getting out are really the range of this function over this interval. So it is that piece of the y-axis, which goes down to 1 and up to 17. That's where this came from. In contrast, though, what is B describing? B is describing a subset of the real numbers, and it's describing the subset of the real numbers with the property that if I square it and add 1 to it, then I end up inside the interval -4 to 3. So, again, I can really think of this in terms of the graph of x squared plus 1. But now I'm talking about a set of inputs to x squared plus 1 where the output ends up between -4 and 3. So if I mark 3 up here and -4 down here, I'm really looking for all of the inputs where the output x squared plus 1 ends up between here and here. So namely, I am looking for that interval. And what is this interval? Well, this interval happens to be -√2 to √2. Note, if x squared plus 1 happens to be in the interval -4 to 3, it also happens to be in the interval 1 to 3. Why? Because x squared is always non-negative, so when I add 1 to it, I get a number that's at least 1. And so that's why I get sort of this skinny piece of the graph that's actually used. So make sure you practice identifying, using, and writing these two kinds of sets, because we're going to be using them a lot throughout the course. Here's a notational aside, and the notational aside concerns this symbol. There are two ways that this symbol is often used. So one of them is what you would probably think, which is that you could use it as a reverse is an element of. And so here, if you read this out loud, this would be z contains 2 as an element. Or just z contains 2, or whatever. Be careful with the word contains, though, because in the abstract, contains could mean subset or element, and those two things are very different. But this is also used sometimes to mean such that. You will never, ever, ever see me do this, because I think it makes everything look horrible, but you would see, for example, some people write this, where they're using this symbol in place of my vertical bar. I, again, would not do this. I think this makes things really hard to read, especially in more complicated sentences, and I really prefer to separate out the equation pieces of the writing, like 3 is an element of z, from the logical pieces, like the such that, and so on and so forth. But you could certainly claim I'm hypocritical in this fashion, because in handwriting, I will just about always write s.t. for such that, so I don't know why that is different, but to me, somehow, that is different. If anything is ever typed, though, you should certainly use the full words such that. Final note on notation concerning this sort of set builder notation business, a lot of people will also prefer to use a colon to a vertical bar. That I have no problem with. If you want to describe the set of squares in that fashion, go right ahead. This is just the set 0, 1, 4, 9, so on and so forth. I think this is more a stylistic thing. It doesn't bother me if people use colons. As a final note about subsets, I want to make sure we distinguish carefully between when something is an element and when something is a subset. So let's take, for example, this set. I'll go ahead and give this set the name A. You'll note, by the way, I'm putting a colon here. The colon means I'm just defining this thing to be that. So A is this set. So let's start by writing down some things that are true. So 1, 3 is, in fact, an element of A. And 1, 3 is a subset of A. Okay. Both of these things are true, but I want to point out they're referring to very different things. When I say 1, 3 is an element of A, I am saying, hey, this particular thing, that one, happens to be in the set. When I say 1, 3 is a subset of A, I am saying both 1 and 3 happen to be in the set. So, in fact, if I take this fact is about that element, whereas this fact is about these elements. So take a minute to decide if these are true. Is 3, 4, 5 an element of A? And is 3, 4, 5 a subset of A? Be sure you think about it, decide on your answers before I write them down. And so here's the answer. Is 3, 4, 5 an element of A? Yes, it is in the list of things that are in A. This is true. Is 3, 4, 5 a subset of A? That's asking, is it true that all of 3, 4, and 5 are elements of A? And it is not. 3 is an element of A, but 4 and 5 are not elements of A. So 3, 4, 5 is not a subset of A. This is my symbol, by the way, for is not a subset. It is just a slash through the whole thing, as opposed to just a slash through the equals. Again, here's a list of 4 statements. Just pause for just a second. You could just do this out loud in your head. Which of these are true and which of these are bogus? So, is the set 2 an element of A? No. And so here it's important to note 2 and the set 2 are different things. So 2, in fact, is an element of A, but the set 2 is not. It is not on the list of things that is here, so this definitely not the case. However, the set 2 is a subset of A, and in fact, the statement, the set 2 is a subset of A, means exactly the same thing as 2 is an element of A. Because if I have what's called a singleton set, that is, a set with one element, and I say that it's a subset of a set, all I'm saying is that that one element is in the set. Okay, so these are both correct. Okay. This, however, is completely bogus. In fact, one could say this is even more bogus than any of the other things that we've said so far. Why? Because what is this claiming? This is claiming 2 is a subset of A, but there's even a more fundamental problem than that it's not the case that every element of 2 is an element of A, and you probably have a sense of what that fundamental problem is. And that fundamental problem is that 2 isn't even a set. So 2 is definitely not a subset of anything. So this distinction is important, especially in writing, and it is very easy to just haphazardly mismatch these pieces. And so you should really think of choosing the correct one between is an element and is a subset. It's really a lot like when you have to choose the right one of there and there, or the right one of your and your. So, similar to how it is important, and yes, it is important, to always write the correct one of each of these pairs, it is important to always write the correct one of these, but it might take you a bit of practice and a bit of thinking consciously about it before you're always putting the right one. In particular, once you have sets whose elements are sets, it's not always the case that when you have a set here, you want subsets. Sometimes you really want an element. There are a bunch of ways, if we have 2 sets, to combine them to get a new set. There are really 4 different ways that we'll talk about to get a new set out of old sets. So the first 2 are union and intersection, which we'll usually write in this fashion. And so the union is really the set of things that are in either set. So the union really sort of matches this logical operator or that we talked about in the last section. And the intersection is the set of things that are in both. This is a set builder notation definition for both of these. Note I haven't put some grand ambient set here, I've just written X's. And so this is really the set of all x that are in A or in B. That's what the union is. Likewise for the intersection. And again, this colon here is saying this is literally the definition of the thing on the left. So when you take the union, this is what you get. When you take the intersection, this is what you get. People often like to think of these things in terms of Venn diagrams. So if I have A and B, and I'm thinking of all the good stuff in A is living inside this circle, and all the stuff in B is living inside this circle, then A union B is just all of these two circles put together. And A intersect B is this overlap between the two of them. Note this picture won't always work because it could well be that A and B share no elements in common, in which case we would say they're disjoint. Okay, and so just to officially write that down as a definition, we say that two sets are disjoint if their intersection is the empty set. The other weird thing that can happen is that, of course, one of the sets can be entirely contained inside the other. And so when this happens, the union is just whatever the outer one is. So here it would be the case, for example, that A union B is B. And so it is a fact that I think you can convince yourself of, but that you'll get to prove on a later homework, that for two sets A and B, A union B is equal to B if and only if A is a subset of B. Next up, we have the set difference, which I'll denote as A minus B. And this is the set of things that are in A that aren't in B. So all of this gets taken away. I'll note people will also write this same thing as A backwards slash B. And so this is another way people will tend to write set difference. I'll tend to use minus. This isn't one that we'll use often, but I will note that especially in computer science, you will often encounter the symmetric difference. And so the symmetric difference, which gets denoted a bunch of different ways, but here's one of them. This is, by definition, A minus B union B minus A. So this would look, in our example, like this. It's worth taking a second to think to yourself, why is this called the symmetric difference? And what is not symmetric about this? And so the thing that's not symmetric here is that if I swap A and B, I get completely different sets. So A minus B is this region, B minus A would be this region. So this minus operator is not symmetric, because if I swap the two sets, then I get a completely different answer. The symmetric difference operator, however, is, as the title would suggest, symmetric. If you flip A and B, you end up defining exactly the same set. Last up is the complement. Note this complement has an E here and not an I here. And so this is something where basically you're supposed to get the stuff that's not in the thing. So A complement is supposed to be the set of things that aren't in A. But there's a problem with that, which is that there's lots of things that are not in A. So I cannot just define the complement to be the things that aren't in A. And so you might, for example, if someone asked you, okay, what is 2, 4 complement? You might imagine, okay, here's my number line. Here's 2, here's 4. So I'm supposed to toss that out. And so the complement will end up being this and that. And so probably a lot of you, if you were asked what's the complement of the closed interval 2, 4, would say, okay, it's minus infinity to 2 union 4 to infinity. Noting that these braces are open because 2 and 4 were in my original set. Here's the problem with this. When you did this, you did not give me all the things that weren't in the closed interval 2, 4. You gave me all the real numbers that weren't in the interval 2, 4. And so your brain read a context into this that if we want to write down a definition for complement, we have to formally state. So whenever you're going to talk about complements, you always need to be thinking about what the sort of ambient space is. And so we call this some sort of universal set. And so if we agree on a universal set, for example, here we probably agreed on the universal set being the real numbers, then the complement, in fact, is just always that universal set minus A. It's the set of all the things that are in the universal set, but not in A. So if you're talking only about real numbers, you'll probably assume the universal set is the set of real numbers. But just as well, you could have the universal set be the positive integers, or the functions from the closed interval 0, 1 to the real numbers that are twice differentiable, or who knows. This set could really be anything. But hopefully, any time that complements come up, it's clear what the universal set is. But I just want to make sure we're clear that the complement is not just the set of all things that aren't in A, because that set would, for example, likely include many zoo animals, and usually we want to avoid putting zoo animals in our sets. They don't like it. All right. So this section has been kind of a whirlwind of terminology related to sets. You'll likely take a bit of time to internalize all of these various pieces. But let's do one more example of this. And I'd encourage you to try and do this by yourself before you watch me do it. So go ahead and look and try and write down these four if A is my open interval from 1 to 3 and B is my closed interval from 2 to 6. Remembering here, the open interval is all the numbers between 1 and 3, excluding 1 and 3. And the closed interval here is all the numbers between 2 and 6, including 2 and 6. Okay, so let's do this. What is A union B? Okay, this is all the numbers that are in either of these sets. So this is going to, in fact, be the interval from 1 to 6. The 1 has this piece of jewelry, and the 6 has this piece of jewelry, because the 6 actually is in the union, but the 1 is not in the union. What about the intersection? Here, I'm looking for all the things that are in both. 2 is the smallest thing that's in both. But then I don't get anything further than 3. Okay, in fact, I don't get 3 either, because 3's in B, but not A. A minus B. This is everything in A that's not in B. 1 up to... And then I'm going to knock out 2. So this is still going to be an open parenthesis over here, because 2 is not included in A minus B. And then B minus A, here I'm going to take away everything up to, but not including 3. So 3 actually is in B minus A. And so I will get here 3, 6. So these are our answers here. Please note, whenever I write down one of these intervals, these things are always subsets of the real numbers, not of the integers. So in particular, this interval here is not 2, 3, 4, 5, 6. This interval includes, for example, numbers like pi and e. So this set here, B, just to go back and echo our terminology from earlier, this set B is infinite. Okay, and all that means is that it has infinitely many elements. I want to do a little bit of practicing putting this section's material together with the previous section's material. So I want to write the negation of some statements involving these. So let's try writing the negation of X is an element of A union B. Now, you could just write X is not an element of A union B, but that turns out not to be super helpful. So the first thing I want to do is re-spell out what this actually says. A union B is the set of things that are in A or B. So this itself, X is in A union B, this means exactly X is in A or X is in B. So what happens when I negate that? This comes back to De Morgan's laws, which is to say that when I negate this, what this actually means is that X is not in A and X is not in B. Remember, when I negate an or statement, it becomes an and statement. Take just a minute. What's the negation of X is in A minus B? Okay, so let's write this down. X is in A minus B. That means X is in A and X is not in B. That was exactly our definition of set minus, right? It was the set of things that were in A that were not in B. So the negation then of X is in A minus B. What is the negation of this? The negation of this is, okay, again, by De Morgan's laws. Okay, so X is not in A and becomes or. And X not in B, what's the negation of that? Okay, well, if X is not in B, then yes, that means X is in B. So in other words, the negation of X is in A minus B is X is not in A or X is in B. Okay, I think we can wrap this video up here. In the next video, we're going to start talking about quantifiers, which are really going to let us put all of these pieces together so we can start making all the kinds of statements of mathematical truth that we'd like to think of in our theorems and propositions and so on. But that's all for now. Until next time, be well.